Everything you see is controlled by forces you cannot see. The cosmos is ruled by hidden powers, from the empty space pushing galaxies apart to the invisible scaffolding holding them together. Today, we are going on a journey through 30 of the most mind-bending theories about these secret forces of the universe. You will walk away with a new understanding of the speculative frontiers of physics, ideas that challenge our most basic assumptions about reality itself. We will explore why the universe's expansion is speeding up, what dark matter might really be, and if we are living in a giant hologram. What is the one theory about the cosmos that makes you question everything you know? Our first stop is the most dominant force in the cosmos, yet we have no idea what it actually is. This is the mystery of dark energy. For decades, scientists believed the universe's expansion was slowing down, a natural coasting after the Big Bang. But in the late 1990s, two separate teams made a shocking discovery. They were observing distant supernovae, the brilliant explosions of dying stars, to measure cosmic distances. What they found was not a slowdown, but a speed up. The universe is not just expanding, it is accelerating. Galaxies are flying apart from each other faster and faster as time goes on. This observation was so revolutionary, it earned the Nobel Prize. To explain this bizarre behavior, physicists turned to an old idea that had been discarded for almost a century: Einstein's cosmological constant. When Einstein was developing his theory of general relativity, his equations described a dynamic universe, one that should either expand or contract. But the scientific consensus at the time was that the universe was static and eternal. To make his theory fit this belief, Einstein added a fudge factor, a repulsive force that would perfectly balance the attractive pull of gravity, keeping the cosmos still. He later called this his biggest blunder. Yet, it turns out, his blunder was a prediction. The cosmological constant is now the leading candidate for dark energy. Think of it not as a substance, but as a property of empty space itself. According to quantum physics, a vacuum is not truly empty. It is a seething, bubbling sea of virtual particles constantly popping in and out of existence. This activity gives the vacuum an inherent energy, a pressure. The cosmological constant proposes that this vacuum energy is uniform and constant everywhere, woven into the very fabric of spacetime. And its effect is a kind of anti-gravity. While gravity pulls matter together, this vacuum energy pushes space itself apart. On the scale of our solar system or even our galaxy, gravity wins. But on the vast, empty scales between galactic clusters, where matter is sparse, this repulsive push takes over, stretching the cosmos faster and faster. The implications are profound and chilling. If dark energy remains constant, as the theory suggests, the acceleration will continue forever. Galaxies beyond our local group will eventually be pushed so far away that their light can never reach us. The observable universe will shrink to a lonely island of stars in an infinite, dark, and ever-expanding void. This is the ultimate fate known as the Big Freeze or heat death, a cosmos where all energy is evenly distributed, all stars have burned out, and all activity grinds to a permanent halt. It is a silent, cold, and eternal end, driven by a force born from nothingness itself. But what if dark matter does not exist at all? What if we are simply misunderstanding the rules of the game? This is the radical proposition of a theory called modified Newtonian dynamics, or MEND. It suggests there is no mysterious, invisible substance holding galaxies together. Instead, the force of gravity itself behaves differently under certain cosmic conditions. The entire case for dark matter rests on a mismatch between what we see and what our equations predict. Look at a spiral galaxy like our own Milky Way. Stars and gas on the outer edges orbit the galactic center at incredibly high speeds. According to Newton's laws of gravity, which work perfectly within our solar system, these outer stars should be moving much slower. The visible mass of the galaxy, all its stars and glowing gas, is simply not enough gravity to keep those fast-moving stars from flying off into intergalactic space. The dark matter hypothesis solves this by adding an enormous, invisible halo of mass, providing the extra gravitational glue. Min takes a different path. It proposes that Newton's famous law of gravity, the one we all learned in school, is not the final word. Instead, at extremely low accelerations, like those experienced in the vast, sparse outskirts of a galaxy, gravity becomes slightly stronger than our standard formulas predict. It is a tiny tweak to the rules, but it is enough to explain why those outer stars orbit so quickly without needing any extra, unseen matter. Imagine driving a car. On a dry, paved road, your brakes work as expected, but on a sheet of black ice, the same pressure on the pedal leads to a completely different and terrifying outcome. Min suggests that gravity, too, has a different set of rules when conditions are extremely faint. A cosmic black ice where accelerations are almost imperceptible. The theory has had some remarkable successes. For many individual galaxies, Min's predictions for their rotation curves match the observed data beautifully, often with more precision than some dark matter models can achieve. It feels elegant, solving the mystery by changing a law rather than inventing a new kind of particle that has stubbornly avoided detection for decades. Yet, the majority of physicists remain skeptical, firmly in the dark matter camp. The controversy centers on evidence that Min struggles to explain. When two galaxy clusters collide, astronomers can map the gravitational landscape by watching how the collision bends light from objects behind it, an effect called gravitational lensing. These observations show that the mass and the visible matter become separated. The hot gas from the clusters, which glows in X-rays, slows down and piles up in the middle of the collision. But the gravitational pull, as mapped by the lensing, stays with the galaxies themselves. This is exactly what you would expect if dark matter were a cloud of particles that simply passes through other dark matter and normal matter without slowing down. For Min to explain this, it would need a complex and perhaps contrived additional tweak, losing its elegant simplicity. Furthermore, the overwhelming evidence from the cosmic microwave background, the afterglow of the Big Bang, shows a specific pattern of tiny temperature fluctuations. Our standard model of cosmology, which includes dark matter, predicts this pattern with stunning accuracy. To date, no modified gravity theory has been able to match this success without also incorporating some form of dark matter. So we are left with a cosmic standoff. One side champions an invisible universe of unknown particles that shape everything we see. The other argues we are using the wrong map, that gravity itself holds a secret we have not yet fully deciphered. The true nature of the universe's hidden architecture remains, for now, an open question. The debate between dark matter and modified gravity forces us to ask a deeper question. Why are the rules of our universe the way they are at all? Why do the fundamental constants, like the strength of gravity or the mass of an electron, have the exact values they do? Tweak any one of them even slightly, and the universe becomes a barren, lifeless void. Stars would not form, atoms would not bond, and life as we know it would be impossible. This cosmic fine-tuning is one of the greatest mysteries in physics. One extraordinary answer suggests we are not asking the right question. Perhaps our universe is not special, nor finely tuned. Maybe it is just one of an almost infinite number of possibilities. This is the theory of the multiverse. Imagine a vast, eternal cosmic foam, bubbling endlessly. Each bubble is a separate universe, inflating into existence with its own unique set of physical laws and constants. In most of these bubbles, the numbers are all wrong. Gravity is too weak to form galaxies, or the nuclear forces are too strong, causing all matter to collapse instantly. These are dead universes, empty and stillborn. But in a rare few, purely by random chance, the numbers line up perfectly. In those bubbles, stars ignite, planets coalesce, and life can emerge. We, of course, find ourselves in one of those rare, hospitable bubbles. This is not a design, but a cosmic selection effect known as the anthropic principle. We observe a universe compatible with our existence because we could not observe one that is not. The multiverse idea is not pure philosophy. It emerges naturally from two of our most successful yet incomplete theories. The first is cosmic inflation, the idea that the early universe underwent a period of exponential, faster-than-light expansion. Many models suggest this inflationary process does not happen just once. It could be eternal, constantly spawning new pocket universes in a never-ending chain reaction, like bubbles continually forming in a pot of boiling water. The second is string theory, a candidate for a theory of everything. String theory allows for a staggering number of possible stable configurations, perhaps 10 to the power of 500. Each configuration corresponds to a universe with different physical properties. This vast landscape of possibilities provides the raw material for the multiverse. If every possible universe exists somewhere, then it is no surprise that one of them looks like ours. This idea is as controversial as it is mind-bending. Critics argue it is not science, but a philosophical surrender. If we cannot interact with, observe, or test these other universes, how can the multiverse theory be falsified? It risks explaining everything, and therefore predicting nothing. Proponents counter that we might find indirect evidence. The violent collisions of these bubble universes in the primordial foam could have left faint scars on the cosmic microwave background, imprints in the oldest light in the sky. Our universe may bear the bruises from collisions with its neighbors in the cosmic foam. The implications are profound. It suggests our entire cosmos, with all its hundreds of billions of galaxies, is just a single bubble in an infinite froth of realities. Every possible version of history, every alternate set of physical laws, may be playing out somewhere in this incomprehensible ensemble. The forces that seem so perfectly tailored for us are not a grand design, but a cosmic accident, a lucky roll of the dice in a game with nearly infinite throws. But if the multiverse is a landscape of possibilities, what is the canvas upon which it is painted? Our entire understanding of the cosmos rests on two magnificent pillars. One is Einstein's theory of general relativity, which paints gravity as the curvature of a smooth, continuous fabric called spacetime. It governs the dance of planets and the expansion of the universe. The other is quantum mechanics, which describes the bizarre, probabilistic world of atoms and particles. Both theories are spectacularly successful in their own domains. Yet, when forced to meet, they break down completely. This conflict is the greatest unsolved problem in fundamental physics. To reconcile them, we need a theory of quantum gravity, a set of rules that describes how gravity works at the smallest possible scales. One of the most promising and beautiful candidates is called loop quantum gravity. Its core idea is radical. It proposes that spacetime itself is not smooth and continuous. It is not a fabric, but a tapestry, and like any tapestry, it is woven from individual threads. In this theory, the very geometry of space is quantized, built from tiny, indivisible loops. These loops, and the networks they form called spin networks, represent the smallest possible units of area and volume. You cannot have half a loop. Space comes in discrete, pixelated chunks. The smooth continuum we experience is an illusion, a blurring together of trillions upon trillions of these fundamental stitches in the cosmic weave. This has a profound consequence for our understanding of cosmic origins. In general relativity, if you rewind the expansion of the universe all the way back, you reach a point of infinite density and curvature called a singularity. This is the Big Bang, a moment where all our equations fail and physics, as we know it, ceases to exist. It is the ultimate edge of reality, but in loop quantum gravity, because space is quantized, there is a smallest possible size. You cannot squeeze matter and energy into an infinitely tiny point. Instead, as you rewind towards the beginning, the density reaches a maximum, and then quantum gravity effects become repulsive. Imagine squeezing a spring. At first, it compresses, but if you push past a certain point, it pushes back with tremendous force. In this theory, the universe did not emerge from a singular point of nothingness. It rebounded. The Big Bang was not a beginning, but a transition. This leads to the stunning concept of the Big Bounce. Our expanding universe could be the aftermath of a great cosmic contraction. A previous universe, perhaps very different from our own, collapsed under its own gravity. But instead of crushing itself into oblivion, it reached a maximum density dictated by the quantum grain of space, and then bounced outward, giving birth to the cosmos we inhabit today. Our entire history, from the first stars to the galaxies we see today, could be just one chapter in an endless, cyclic story of cosmic death and rebirth. The visual representation of this quantum spacetime is called a spin foam. Picture the spin network not as a static web, but as a dynamic, foamy structure evolving through time. Each bubble in this foam represents a quantum event, a discrete change in the geometry of space. The history of the universe is not a smooth movie, but a flipbook of these fundamental quantum transitions. It is a universe built from logic and loops, where the fabric of reality has a finite, woven texture. While still a work in progress, loop quantum gravity offers a vision of a universe without true edges or singularities, a cosmos where space itself is born from a deeper, more fundamental quantum architecture. Yet if spacetime is woven from loops, what are the threads themselves made of? This question leads us to one of the most ambitious and elegant frameworks in all of physics, string theory. Its core proposition is both simple and revolutionary. At the most fundamental level, the universe is not composed of point-like particles. Instead, the basic ingredients are unimaginably tiny, vibrating strands of energy, or strings. Think of the strings on a violin. A violin string can vibrate at different frequencies, and each frequency produces a distinct musical note. In string theory, each distinct vibration pattern of a fundamental string corresponds to a different particle. One specific vibration gives you an electron. Another, slightly different resonance produces a quark. The photon, the particle of light, is another note in this cosmic symphony. In this view, all the forces and all the matter in the universe are harmonies played on these tiny, one-dimensional strings. The theory's power comes from its ability to naturally include gravity. Among the possible vibrations, string theory predicts one that has the exact properties of the graviton, the hypothetical quantum particle that would carry the gravitational force. For the first time, gravity is brought into the quantum fold, not as an add-on, but as an inevitable consequence of the string's music. But there is a catch, and it is a spectacular one. The mathematics of string theory only works if the universe has more than the 3 spatial dimensions we experience. It requires either 10 or 11 dimensions for its equations to be consistent. So where are these extra dimensions? The theory suggests they are curled up or compactified at every single point in space, at a scale so small we could never hope to perceive them directly. Imagine a long, thin garden hose. From a great distance, it looks like a simple one-dimensional line. But if you get very close, you see it has a second dimension, a circular cross-section, curled tightly around its length. In string theory, our entire 3-dimensional space could be like that hose, with 6 or 7 extra dimensions curled into incredibly complex, tiny shapes at every location. These shapes are known as Calabi-Yau manifolds. The specific geometry of these hidden dimensions is everything. It determines how the strings vibrate within them, which in turn dictates the laws of physics in our visible, 3-dimensional world. The mass of an electron, the strength of the nuclear forces, even the number of particle generations, all could be locked into the topology of these unseen, compactified dimensions. This leads to string theory's greatest strength and its most profound weakness, the landscape problem. The mathematics allows for a staggering number of possible Calabi-Yau shapes, perhaps 10 to the power of 500. Each shape corresponds to a universe with a different set of physical constants and laws. This is the string theory landscape, a vast cosmic catalog of possible realities. It provides a potential mechanism for the multiverse, but it also means string theory does not predict one unique universe like ours. It predicts nearly all of them. This makes the dream of a single, testable theory of everything incredibly difficult. If any possible universe can exist within the landscape, how do we find evidence for our specific one? Some physicists hope for signatures in particle colliders, like the Large Hadron Collider, perhaps in the form of supersymmetric particles, a key prediction of many string models. Others look to the cosmos, searching for imprints of the strings themselves in the faint ripples of gravitational waves from the earliest moments of time. For now, string theory remains a magnificent, untested symphony of mathematics, a vision of a universe where the deepest truths are written not in particles, but in vibrations, and where every law of nature is a melody played on the hidden geometry of extra dimensions. This vision of a universe woven from vibrating strings leads to an even more radical idea about information itself. What if every single event, every particle, every force within a region of space is not truly happening within that volume, but is instead a projection from its outer surface? This is the holographic principle, a theory that redefines the very nature of reality. It proposes that our 3-dimensional world, with all its rich depth and complexity, might be akin to a hologram, a magnificent illusion generated from information encoded on a distant, 2-dimensional screen. The roots of this astonishing idea are found in the most extreme environments in the cosmos, black holes. In the 1970s, physicist Jacob Bekenstein made a profound connection. He realized that a black hole's event horizon, the point of no return, has a property very similar to entropy, a measure of disorder or information content. Stephen Hawking later showed that black holes are not completely black. They emit a faint glow of radiation due to quantum effects near the horizon, and they can slowly evaporate. This created a paradox. If you throw an object, say a book filled with information, into a black hole, it vanishes behind the horizon. Eventually, the black hole evaporates through Hawking radiation, which appears to be random and featureless. What happened to the information contained in that book? According to the laws of quantum mechanics, information can never be truly destroyed. This is the black hole information paradox. The holographic principle emerged as a potential solution. It was first proposed by Gerard T. Hooft and later developed by Leonard Susskind. Their revolutionary insight was this: all the information that falls into a black hole is not lost inside its mysterious interior. Instead, it is perfectly encoded, scrambled, and stored on the two-dimensional surface of the event horizon. The three-dimensional volume of the black hole is an illusion. The true description of everything within it exists on its boundary. Think of a holographic sticker on your credit card. The flat, shiny surface contains a pattern of microscopic grooves. When light hits it, your brain interprets that flat pattern as a stunning, three-dimensional image floating in space. The holographic principle suggests our universe operates on a similar, but far grander scale. The entire cosmos we experience, every galaxy, every planet, every one of us, could be a projection from a vast, two-dimensional surface at the edge of observable space. In this view, gravity and the three-dimensional world are not fundamental. They are emergent phenomena, side effects of quantum information processing happening on a distant, lower-dimensional screen. This idea finds a concrete mathematical home in a concept called the anti-de Sitter conformal field theory correspondence, often abbreviated as AD-S-CFD. It is a duality, a perfect dictionary, between a universe with gravity, like ours but with a specific geometry, and a quantum field theory without gravity that lives on its boundary. Calculations that are impossibly difficult in the gravity-filled, three-dimensional world can become straightforward problems in the two-dimensional quantum theory, and vice versa. It is as if the entire, complex story of a three-dimensional movie is contained entirely in the barcodes on the edge of the film reel. While our actual universe may not perfectly match the specific AD-S geometry used in these models, the principle stands as a powerful clue. It hints that gravity itself may not be a fundamental force, but a thermodynamic force, an entropic effect that arises from the way information is organized on the cosmic horizon. If the holographic principle is correct, our perception of depth, of volume, of being inside a three-dimensional reality is a magnificent trick of the light. We are living inside the world's most convincing illusion, a cosmic projection where every star, every thought, and every law of physics is rendered in real time from a simpler, flatter, more fundamental reality. Yet if the holographic universe is an illusion, what then is casting the shadow? For decades, the leading suspect has been a ghostly particle that permeates every corner of space. These are the weakly interacting massive particles, or WIMP. This is the classic, elegant candidate for dark matter, and it hinges on a beautiful piece of cosmic serendipity. In the early universe, a fraction of a second after the Big Bang, a primordial soup of particles and radiation was constantly colliding and interacting. As the cosmos expanded and cooled, most particles, like the protons and electrons that make up our bodies, fell out of this thermal bath and froze into existence. theorists realized that a stable, massive particle that interacted only through gravity and the weak nuclear force, one of the fundamental forces governing radioactive decay, would naturally fall out of equilibrium at just the right moment. The calculations showed that the relic density of such particles left over from the Big Bang would almost perfectly match the amount of dark matter we observe in the universe today. This remarkable alignment is known as the WIMP miracle. It suggested that dark matter was not an arbitrary invention, but a necessary prediction from the same physics that governs the known particles. Imagine a cosmic crime scene where the culprit's shoe size, estimated from a footprint, matches perfectly with a suspect who was already in the building for a completely different reason. That is the compelling case for WIMP. They would be everywhere, a vast cloud passing through our planet, our homes, and even our bodies, utterly unnoticed because they so rarely bump into ordinary matter. To catch one, you need to build the quietest, most shielded detectors on Earth. This is why scientists go deep underground, into abandoned mines or beneath mountains. They are building traps of incredible sensitivity, shielded from the constant barrage of cosmic rays that would drown out the faint signal. One of the most famous experiments is the Large Underground Xenon Experiment, or LUX. Its core is a tank of ultra-pure liquid xenon, chilled to extreme temperatures and watched by arrays of sensitive light sensors. The idea is simple in principle. If a WIMP from the galactic dark matter halo happens to drift through the tank, there is a tiny chance it will collide with the nucleus of a xenon atom. That collision would produce a faint flash of light and a small charge of electricity. Detecting that dual signal amidst a sea of background noise is the monumental challenge. For years, these experiments have grown larger and more sensitive, from LUX to its successor, Lux Zeppelin, and others around the world. They have ruled out vast swaths of possible WIMP masses and interaction strengths. Yet, the ghost has not been caught. The detectors remain silent. This profound non-detection is forcing a major rethink. The WIMP miracle, while elegant, may have been a cosmic coincidence. Perhaps dark matter particles are even more elusive, interacting only through gravity, making them virtually impossible to detect with our current methods. Or maybe they are not particles at all, but something even stranger, like primordial black holes formed in the universe's first moments. The search continues, a high-stakes game of hide and seek played in the deepest quiet of the Earth, where scientists listen intently for a whisper from the hidden majority of the cosmos. The profound silence of the WIMP detectors has sent physicists searching for a ghost of a different kind. Enter the action, a dark matter candidate born not from cosmic necessity, but from a deep puzzle within the heart of the atom itself. This story starts with a mystery of symmetry. The strong nuclear force, which glues protons and neutrons together, has a curious property. In theory, its equations allow for a violation of a symmetry known as CP, which would cause the neutron, a neutral particle, to possess a tiny electric dipole moment. Think of the neutron as a microscopic bar magnet. This symmetry violation would give it an imbalanced shape, a positive charge shifted slightly from a negative one. Yet, incredibly precise experiments have found no such distortion. The neutron is perfectly symmetric to an astonishing degree. Why does the strong force respect this symmetry so perfectly when it has no apparent reason to? To solve this, physicists proposed a new particle, the action, a lightweight field that would naturally sweep this imbalance under the cosmic rug, restoring perfect symmetry. The action was a solution to a particle physics problem, but it soon revealed a cosmic secret. If actions exist, they would have been produced in colossal numbers in the hot, dense early universe. And crucially, they are predicted to be stable, cold, and most importantly, incredibly light. Where a WIMP might be hundreds or thousands of times heavier than a proton, an action could be billions or even trillions of times lighter. This fundamental difference changes everything. You would not have individual, bullet-like particles drifting through space. Instead, you would have an ocean. Because of their quantum nature, these ultra-light particles would behave less like discrete specks and more like a pervasive, invisible field oscillating throughout the cosmos. Imagine the entire universe submerged in a gentle, cosmic hum, a wave of incredibly low frequency passing through every atom. This collective vibration is what we would perceive as the action dark matter halo. Detecting such a wispy entity requires a completely different kind of hunt. You cannot wait for a rare collision in a vat of xenon. Instead, you must try to coax the action field to reveal itself, to make it sing. The most promising method uses a powerful tool, the action haloscope. At its heart is a strong magnetic field. The theory predicts that in the presence of such a field, an action should have a tiny chance to convert into a photon, a particle of light. So, scientists build what is essentially a highly sensitive radio receiver inside a massive magnet. They tune this cavity, searching across a wide range of frequencies, listening for an anomalous whisper of microwave photons that cannot be explained by any known source. It is like trying to find one specific, faint radio station in a universe of static by slowly turning a dial, hoping to hear a signal that appears only when your magnet is powered on. Experiments like the Action Dark Matter Experiment, ADMX, are doing exactly this, operating at temperatures colder than deep space to silence any thermal noise. The search is painstaking as the possible mass, and thus frequency, of the action is not precisely known. But if found, it would be a double discovery, solving both a decades-old particle puzzle and the greatest mystery in cosmology. Compared to the heavy, crashing particle concept of WIMP, the action paints a more ethereal picture of dark matter, not as scattered rocks, but as a silent, all-pervasive tide, its gentle pressure sculpting the galaxies from within. The search for dark matter has turned to relics from the very dawn of time. One audacious theory suggests the missing mass of the universe is not a sea of particles, but a swarm of ancient corpses, black holes born in the first chaotic moments of creation. These are primordial black holes, and if they exist, they could rewrite the story of dark matter and the cosmos itself. Unlike the stellar black holes we know, formed from the collapse of massive stars, primordial black holes are thought to have been forged in the extreme density fluctuations of the infant universe, less than a second after the Big Bang. In that seething, hot plasma, regions of space that were just a fraction denser than their surroundings could have collapsed directly under their own gravity, punching holes in the fabric of spacetime. These objects would have a staggering range of possible sizes, from the mass of a small asteroid to many times the mass of our Sun. The most compelling candidates for dark matter fall into two categories. One is asteroid mass black holes, trillions of which could be drifting through our galaxy like a fine, invisible dust. The other is in the range of tens of solar masses, precisely the size range detected by gravitational wave observatories like LIGO and Virgo. When these instruments first heard the chirp of two black holes merging, it sent a shock wave through astrophysics. The black holes were too heavy to have formed easily from stars in the universe's current era. Could they instead be primordial, ancient fossils from the beginning of everything? Finding them requires clever detective work, For the smaller asteroid mass black holes, scientists use a technique called gravitational microlensing. If such a black hole passes directly between Earth and a distant star, its gravity will act as a lens, bending and focusing the star's light. For a brief period, the star will appear to brighten, then fade in a distinctive symmetric pattern. Massive surveys scanning millions of stars have found such events, but not nearly enough to account for all dark matter. The heavier black holes leave a different signature, the ripples in spacetime from their violent mergers. The population and masses of black holes seen by LIGO could be a fossil record of the conditions in that first fraction of a second. If a significant portion of dark matter is locked inside these primordial objects, it changes our understanding of the early universe dramatically. It suggests the cosmos was born with a specific, lumpy texture, a roughness imprinted by quantum processes operating at energies we can scarcely comprehend. These black holes would have been some of the first structures to form, seeding the growth of galaxies that came later. They are a direct link to a time before the first stars, a hidden architecture woven into the cosmos from its very first breath. But if the cosmos can bounce and strings can vibrate, could our entire universe be just one sheet in a higher dimensional stack? This is the breathtaking vision of the ekpyrotic and cyclic universe, a theory that does away with the Big Bang singularity entirely. In this model, our three-dimensional universe is not all there is. It is a three-dimensional membrane, or brain for short, floating within a larger, higher dimensional space called the bulk. Picture our cosmos not as an expanding bubble, but as a vast, flat sheet, like a page in a book. And just like in a book, there could be other pages, other brains, parallel to our own, separated by a tiny gap in an extra dimension. The story begins not with a bang, but with a near miss. In the cyclic version of this theory, our brain and a parallel brain are drawn together by a force across the bulk, moving on a slow, cosmic timescale. They do not collide head-on, but rather brush past each other, like two sheets of paper gliding alongside one another. This close encounter transfers an enormous amount of kinetic energy into our brain. From our three-dimensional perspective, trapped on the sheet, this influx of energy looks like a universe filled with an intensely hot, dense plasma of particles and radiation. We would interpret this event as our Big Bang. It was not an explosion from a point, but a fiery awakening caused by a gravitational kiss from a neighboring reality. This solves the singularity problem elegantly. There is no point of infinite density because the universe existed before the collision, cold, empty, and contracted. The hot Big Bang was simply a phase transition, a moment of heating and expansion triggered by an external event. After the brains separate, our universe expands and cools, much as we observe, forming galaxies and stars over billions of years. But the story does not end there. This is a cyclic model. The same force that drew the brains together will, over an almost unimaginable timescale, pull them back for another encounter. The universe will eventually stop expanding, contract very slowly, and then be reignited by the next collision, birthing a new cosmic cycle from the ashes of the old. This stands in stark contrast to the standard inflationary Big Bang, which begins with a singularity and leads to a universe destined for eternal, lonely expansion. The cyclic universe offers a different destiny, an endless, rhythmic dance of creation and renewal. The energy for each new cycle comes not from nothing, but from the gravitational potential energy between the brains themselves, a cosmic battery that never runs down. To visualize this, think of the bulk as a calm, dark ocean. The brains are like immense, invisible rafts on the surface. They are pulled together by a gentle current. They scrape against each other with a shower of sparks that we call our universe, and then they drift apart, only to be drawn together again eons later. This elegant framework emerges naturally from string theory, where such brains are fundamental objects. It paints a cosmos of astonishing grandeur, where our entire history is just one act in a play with no beginning and no end, a timeless symphony written on colliding sheets of reality. This endless cosmic cycle rests on a profound assumption that the very fabric of our universe is stable. But what if it is not? Quantum field theory, our most successful description of the subatomic world, paints a startling picture of reality's foundation. It suggests the universe exists in a state of minimum energy, what we call the vacuum. This is not empty nothingness, but the lowest possible energy configuration of all the quantum fields that permeate space. Our laws of physics, from gravity to electromagnetism, are the rules of this particular vacuum state. But there is a terrifying possibility. We may not be in the true lowest energy state. We could be trapped in a false vacuum, a local minimum, like a ball resting in a shallow dip on the side of a much deeper valley. The situation is stable for now. The ball would need a quantum kick to roll over the lip and into the abyss. But given enough time, quantum mechanics tells us such an event is not just possible, but inevitable. Somewhere, perhaps in the vast emptiness between galaxies, a random quantum fluctuation could provide that kick. A tiny bubble of true vacuum would spontaneously form. Inside this bubble, the laws of physics would be completely different. The fundamental constants might change, atoms could not hold together, and matter as we know it would cease to exist. And this bubble would not stay small. The energy difference between the false vacuum outside and the true vacuum inside creates an immense outward pressure. The bubble's wall would expand in all directions at the speed of light. Nothing could outrun it, and nothing could survive its passage. As the wall of true vacuum sweeps through space, it rewrites reality itself, converting the unstable false vacuum into the stable, but alien true state. From our perspective, the end would come without warning. One moment, the universe is as it always was. The next, a sphere of annihilation appears, perhaps light years away. We would see nothing until the wall arrived, because the first signal of its coming would be the wall itself, traveling at light speed. There would be no flash, no sound, just an instantaneous and total transformation of everything, from the largest galaxy to the smallest thought, into something utterly unrecognizable. The cosmos would continue, but it would no longer be our cosmos. This is vacuum decay, the ultimate cosmic doomsday scenario. It is not a collision, an explosion, or a freeze. It is an erasure, a correction to a fundamental mistake in the universe's underlying code. The theory emerges directly from the mathematics of the Higgs field, the same field that gives particles their mass. Our measurements suggest the Higgs could indeed be in a metastable state, making this scenario more than just science fiction. It is a legitimate, though highly speculative, prediction of our best theories. The silver lining, if it can be called that, is the timescale. The half-life of our false vacuum could be longer than the current age of the universe by a factor of billions upon billions. The probability of it happening in any given region of space at any given moment is astronomically small. Yet in an infinite or near-infinite universe, given infinite time, the improbable becomes certain. It is a reminder that our reality, for all its apparent solidity, rests on a quantum foundation that is inherently precarious, a temporary arrangement in a landscape of possibilities we can scarcely comprehend. The precarious nature of our cosmic foundation forces us to look back to the very beginning. How did our universe achieve its immense size, stunning smoothness, and intricate structure in the first place? The answer is a theory of breathtaking speed and power, cosmic inflation. In its first moments, the universe did not just expand, it exploded in scale at a rate far beyond the speed of light. This was not an expansion of matter into space, but a stretching of space itself, a hyper-fast smoothing and flattening of the entire cosmos. For a fleeting fraction of a second, a single subatomic volume of space ballooned to become larger than our entire observable universe today. This radical idea solves two profound puzzles that the standard Big Bang model could not. The first is the horizon problem. Look at the cosmic microwave background, the ancient afterglow from when the universe became transparent. Its temperature is almost perfectly uniform in every direction we look. But in the classic Big Bang, there had not been enough time for light, or heat, to travel from one side of the early cosmos to the other to equalize that temperature. Distant regions should never have been in contact, yet they are in perfect thermal equilibrium. It is as if you walked into a vast auditorium where people in opposite corners, who have never met or spoken, are wearing identical outfits down to the smallest detail. Inflation solves this by proposing that these distant regions were once intimately connected, crammed into that tiny, pre-inflationary volume. They had plenty of time to reach a uniform temperature before the hyper-fast expansion ripped them apart, stretching them to opposite ends of the sky. The second puzzle is flatness. The geometry of our universe, as best we can measure, is incredibly flat, like a perfectly smooth sheet of paper. In the early universe, even the tiniest deviation from perfect flatness would have been magnified by billions of years of expansion, leading to a cosmos that is either catastrophically closed and collapsed, or radically open and empty. For our universe to be as flat as it is today, its initial conditions had to be fine-tuned to an absurd degree of precision, like balancing a pencil on its tip for 14 billion years. Inflation acts as a cosmic iron. No matter what shape the universe started with, that explosive stretching smooths out any wrinkles and flattens any curvature, leaving behind the vast, flat expanse we observe. The engine for this incredible event is thought to be a hypothetical quantum field called the inflaton field. Picture it as an invisible energy field that permeated all of space. In the very beginning, this field was trapped in a high energy state, like a ball perched at the top of a very flat plateau. This high energy state exerted a tremendous negative pressure, causing space to stretch at an exponential rate. As inflation proceeded, the inflaton field slowly rolled down its energy hill. When it finally reached the bottom, the immense stored energy was released in a fiery burst, repopulating the universe with the hot soup of particles that would become the Big Bang's afterglow. But here is the most beautiful part. During inflation, the inflaton field was not perfectly smooth. It was subject to tiny quantum fluctuations, random jitters at the smallest scales. As space inflated at fantastic speeds, these microscopic ripples in the field were stretched to astronomical sizes. Regions with slightly higher energy density expanded just a bit slower, becoming the seeds for future gravitational collapse. Regions with slightly lower density became the vast cosmic voids. These quantum wrinkles, magnified across the cosmos, became the blueprint for all structure in the universe. Every galaxy, every star, every planet owes its existence to those random tremors in the inflaton field during that first fleeting moment. The evidence for this theory is written in the oldest light we can see. The cosmic microwave background is not perfectly smooth. It contains tiny variations in temperature, a speckled pattern that matches the predictions of inflation with remarkable accuracy. But scientists are hunting for a more specific signature, a faint imprint in the polarization of this ancient light. As gravitational waves from the inflationary period rippled through the fabric of spacetime, they would have left a distinctive swirling pattern, or B-mode polarization, in the microwave background. Finding this pattern would be a smoking gun for inflation. Experiments at the South Pole and in space are scanning the skies with incredible sensitivity, trying to detect this whisper from the universe's first trillionth of a second. It is a search for the fingerprint of creation, a direct link to the moment when quantum uncertainty was blown up to become the grand architecture of the cosmos. The quantum seeds of our universe feel impossibly real, but what if they are part of an even deeper layer of code? This brings us to a theory that is as unsettling as it is compelling, the simulation hypothesis. It proposes that our entire universe, from the farthest galaxy to the feeling of sunlight on your skin, is not a fundamental reality, but an incredibly sophisticated computer simulation, a cosmic virtual reality run by an advanced civilization. It is an ancient philosophical idea, Plato's cave for the digital age, but in recent decades it has gained serious traction among some philosophers, physicists, and even tech entrepreneurs. The argument often begins with the unnervingly mathematical nature of our reality. The laws of physics are not just described by mathematics, they seem to be written in it. From the elegant equations of general relativity to the probabilistic rules of quantum mechanics, the universe operates with a precision that feels algorithmic. As physicist Max Tegmark has suggested, our physical reality could be a mathematical structure. If that is the case, then it is, in principle, computable. It could be rendered. Furthermore, we are already creating simulated worlds of increasing complexity. Our video games now host vast, persistent universes with their own physics and ecosystems, inhabited by millions of players. If our technological civilization continues to advance for 1,000 or 1,000,000 more years, the computing power required to simulate an entire universe, or even a vast ensemble of them, could become trivial. Now, follow this logic to its conclusion. If it is possible for an advanced civilization to create such simulations, and if they have any interest in running them, they would likely create a staggering number of them. There could be billions of simulated universes for every one base reality. If that is true, then statistically, the odds are overwhelming that we are not in the original reality, but in one of the countless simulations. We are far more likely to be a line of code than a biological entity in the foundational universe. This is a modern version of the anthropic principle, the simulation argument. The philosophical implications are dizzying. If this is a simulation, then the constants of nature are not discovered. They are parameters. The speed of light, the strength of gravity, these could be variables set by the programmers. The bizarre, counterintuitive rules of quantum mechanics, where particles exist in multiple states until observed, could be a clever optimization technique, a way for the simulation to only render detail when it is being looked at, saving immense computational resources. Even our own consciousness could be a convincing subroutine. Searching for proof is a challenge, but some scientists suggest looking for glitches in the matrix, subtle signs of low resolution or computational shortcuts in the fabric of reality. These might appear as anomalies in the cosmic microwave background, strange violations of energy conservation, or inexplicable limits in high-energy particle collisions. The simulation hypothesis forces a profound reevaluation of existence. It suggests that the quest for a theory of everything may not be a search for fundamental truth, but a reverse engineering of the simulation's source code. It blurs the line between reality and illusion, asking us to consider that the forces we have been exploring, from dark energy to quantum loops, may not be laws of nature, but the elegant, rendered effects of a program running on a computer of unimaginable scale in a reality we can never see. The simulation hypothesis makes a startling claim about the nature of our reality. But what if the very force that holds that reality together is also an illusion? This is the radical proposition of emergent gravity, a theory that suggests gravity is not a fundamental force of nature at all. It is not woven into the fabric of space-time like the other forces. Instead, it is a side effect, a collective behavior that arises from something deeper, much like the concept of temperature. Temperature is not a property of a single atom. You cannot point to one particle and ask for its temperature. It is an emergent property, a statistic that describes the average motion of countless particles in a system. Gravity, according to this view, may be the same, a macroscopic phenomenon that emerges from the complex interactions of countless bits of quantum information. The most prominent version of this idea comes from physicist Eric Verland, who calls it entropic gravity. His starting point is a deep connection between gravity and thermodynamics, the science of heat and disorder. The key is entropy, a measure of the number of ways a system can be arranged. Verland proposed that gravity is not an attractive force pulling masses together, but a consequence of nature's tendency to maximize entropy, to move toward disorder. Imagine the vacuum of space as a sea of fundamental bits of information. When you place a massive object, like a star, into this sea, it displaces these informational bits. The region around the star now has a different entropy, a different level of disorder, compared to empty space. According to Verland's mathematics, the natural tendency for entropy to increase then causes these informational bits to push back, to reorganize in a way that draws other objects toward the star. It looks like attraction, but it is really a statistical drift toward higher entropy. This perspective offers a breathtakingly different explanation for dark matter. Recall the problem stars orbit galaxies too fast, implying there is extra, unseen mass providing gravity. In Verland's framework, there is no need for invisible particles. The extra gravitational effect, what we call dark matter, emerges naturally from the way the quantum information in the universe is entangled and organized on large scales. The visible matter of stars and gas interacts with this underlying informational sea, and the collective behavior of that sea produces a stronger gravitational pull in galactic outskirts than Newton's laws would predict. It is not extra mass, but extra entropy. This idea is deeply entwined with the holographic principle. If our three-dimensional reality is a projection from a two-dimensional surface, then gravity and space itself are not primary ingredients. They are phenomena that emerge from the quantum information processing happening on that distant boundary. In this view, gravity is essentially a thermodynamic force, an entropic push that arises from the way information is stored and updated on the cosmic hard drive. Visualize the universe not as a smooth fabric, but as a dynamic, shimmering network of quantum entanglement links. Each link represents a connection between bits of information. The structure of this network, its density and connectivity, defines the geometry of space, and where this network becomes more complex or dense, it creates what we perceive as a gravitational field. A massive object is a place where the web of entanglement is profoundly altered, creating a gradient that other objects naturally follow. It is a universe where the force that binds planets and stars is not a fundamental tug, but a statistical tendency, a cosmic drift toward disorder that, ironically, creates the most beautiful structures we know. The theory remains highly speculative and faces significant mathematical and observational challenges, but it represents a profound shift in thinking, suggesting that the most familiar force in our daily lives may be the ultimate emergent illusion, a ghostly effect dancing on the surface of a deeper, information-based reality. Emergent gravity suggests the forces we perceive may be illusions of a deeper order. But what if time itself, that relentless forward march, could also crystallize? This brings us to one of the most bizarre and beautiful concepts in modern physics, the time crystal. A crystal, like a diamond or a snowflake, is defined by its repeating pattern in space. Its atoms are arranged in a lattice that repeats at regular intervals. A time crystal does something seemingly impossible. It exhibits a repeating pattern in time. In its ground state, its state of lowest energy, it does not sit still. It perpetually oscillates, ticking like a clock without ever being wound, breaking what physicists call time translation symmetry. This is not a machine. It is a new phase of matter, as distinct from a solid or a liquid as a solid is from a gas, but its order is temporal, not spatial. The theoretical possibility was first proposed by Nobel laureate Frank Wilczek in 2012. The idea was met with immediate skepticism. Perpetual motion in the ground state seemed to violate fundamental thermodynamic principles. How could a system at its lowest energy state be constantly moving without any energy input? The resolution is as subtle as it is profound. In a true time crystal, the motion does not produce any usable work. It does not violate the laws of thermodynamics because it is not an engine. It is a clock whose ticking is locked into the quantum structure of the system itself. The breakthrough came in the laboratory. In 2017, two separate teams, one using a chain of ytterbium atoms, the other using defects in diamond, created the first experimental time crystals. They did not build a tiny perpetual motion machine from scratch. Instead, they took a quantum system and gave it a specific rhythmic kick, like tapping a pendulum at just the right moment. But then, something remarkable happened. When they varied the timing or strength of the kicks, the system's response did not follow precisely. The time crystal's oscillation period was locked in, robust against perturbations. It had settled into its own rhythmic beat, a temporal echo that persisted because of quantum entanglement linking the particles together. Visualize it not as gears turning, but as an atomic dance. A row of atoms, each like a tiny magnet or spin, initially pointing in random directions. After the initial pulse, they do not just flip and settle. They enter a coordinated, endless loop. The entire chain flips in a precise sequence, then flips back over and over, its pattern repeating not in the space between atoms, but in the ticks of an abstract clock. This is order in the fourth dimension. The implications ripple out in two extraordinary directions. First, for our understanding of time. The arrow of time, its relentless forward direction, is tied to increasing entropy, the move from order to disorder. Yet here is a system that, in its ground state, maintains a rhythmic order forever. It is a stable pattern in the flow of time itself, a hint that time may have a granular, structured quality we are only beginning to perceive. Second, and more practically, time crystals could be a revolutionary tool for quantum computing. The greatest challenge in building a quantum computer is decoherence, the tendency for fragile quantum states to be destroyed by the slightest disturbance from the outside environment. A time crystal's robustness, its locked-in rhythm, could provide a protected subspace within a quantum processor. Qubits of information encoded in the crystal's oscillations might be shielded from noise, acting as a perfect, stable memory for a quantum machine. It is a tantalizing prospect, harnessing a new phase of matter to build the computers of the next century. The time crystal shows us that the universe's hidden forces are not just about pushing and pulling in space. They can be about rhythm and resonance in time, revealing that even in its lowest energy state, the quantum world is never truly still. The time crystal's endless rhythm hints at a deep stability in the quantum world, but that stability faces its ultimate test at the edge of a black hole. Here, the two great pillars of physics, quantum mechanics and general relativity, clash in a conflict so fundamental it threatens to rewrite the rules of reality. This is the black hole information paradox, a puzzle that asks a deceptively simple question. When something falls into a black hole, what happens to the information it contains? Think of a book. It is made of atoms, but its true essence is the specific arrangement of those atoms, the words and ideas printed on its pages. That arrangement is information. According to the bedrock principle of quantum mechanics, information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is called unitarity, and it is the law that allows the past to be logically connected to the future. General relativity, however, paints a different picture. When an object crosses a black hole's event horizon, it is lost forever to the outside universe. The black hole's only properties, according to the famous no-hair theorem, are its mass, electric charge, and spin. All other details, the book's title, the color of its cover, the story it tells, are erased. The information is gone, swallowed by the singularity. For decades, physicists accepted this grim fate. Then, Stephen Hawking made a discovery that turned the paradox into a crisis. He showed that black holes are not completely black. Due to quantum effects near the event horizon, they emit a faint glow of particles, now called Hawking radiation. This radiation is thermal, meaning it is random and featureless, like the heat from a stove. It carries away energy, causing the black hole to slowly shrink and eventually evaporate completely. And here lies the paradox. If the black hole evaporates, leaving behind only this random thermal radiation, then all the information about everything that ever fell into it has been permanently erased from the universe. The book is not just burned, its ashes are scattered into a formless, random haze. Quantum mechanics says this is impossible. This is the information paradox. One radical proposal to solve it is the firewall paradox. If information is to escape, perhaps it does so in a violent burst at the horizon itself. The idea suggests that the event horizon is not a smooth, empty space as general relativity predicts, but a searing wall of high-energy particles, a literal firewall that incinerates anything trying to cross. This would preserve information by releasing it in the fire, but it completely contradicts Einstein's picture of an uneventful fall through the horizon. For an astronaut, the difference is catastrophic. According to relativity, you would cross the horizon without noticing anything special, at least until tidal forces pulled you apart later. According to the firewall, you would be vaporized instantly. Both theories cannot be right. Modern physics is seeking a middle path, and one promising avenue involves a concept called quantum hair. This suggests that black holes do have more subtle properties than mass, charge, and spin. When an object falls in, it imprints extremely faint quantum signatures on the gravitational field around the black hole, like a unique fingerprint in the fabric of spacetime. This quantum hair could encode the lost information, making it accessible from the outside, perhaps in the correlations within the Hawking radiation itself. Another profound idea comes from the holographic principle and is known as islands in the gravitational path integral. This complex framework suggests that information that falls into a black hole is not stored deep inside. Instead, it becomes encoded on extremely complex, entangled quantum surfaces that appear like islands in the region near the event horizon. As the black hole evaporates, these islands allow the information to gradually leak back out, woven into the seemingly random Hawking radiation. To an outside observer, the information never actually entered the black hole. It was just scrambled and stored on these quantum surfaces, waiting to be retrieved. The resolution matters because at its heart, this is a battle for the soul of physics. If information can be lost, then the universe is fundamentally unpredictable. The chain of cause and effect is broken, and reality becomes inherently fuzzy. Preserving information is preserving the logical structure of the cosmos itself. It assures us that the universe is a system that can, in theory, be understood, where history leaves a permanent, if deeply hidden, mark. The black hole is the ultimate laboratory, testing whether our laws of physics can survive their own most extreme predictions. The black hole's paradox reveals a universe where information is sacred. But what about particles that are born from information's absence? Neutrinos are the ghosts of the particle world, streaming through you by the trillions every second, yet they pass through the entire Earth as if it were not even there. For decades, physicists believed these elusive particles were massless, traveling at the speed of light and never changing. But nature had a stunning surprise in store, one that forced us to rewrite the rulebook. It is called neutrino oscillation. A neutrino is not born with a fixed identity. It comes in three types or flavors: electron, muon, and tau. Think of them as three different costumes a single actor can wear. An electron neutrino is produced in the heart of the sun, during nuclear fusion. According to the original theory, it should stay an electron neutrino forever. But experiments told a different story. Detectors on Earth built to catch these solar neutrinos consistently found only about 1/3 of the expected number. Where did the rest go? They did not vanish. They changed costumes. As a neutrino travels through space, it oscillates, morphing from one flavor into another. An electron neutrino leaving the sun might arrive at Earth as a muon or tau neutrino. This simple, beautiful phenomenon has a profound implication. For oscillation to be possible, neutrinos must have mass. A tiny, almost imperceptible amount of mass, but mass nonetheless. This discovery shattered the standard model of particle physics, which had assumed neutrinos were massless. It was the first clear crack in that otherwise perfect edifice, a sign of physics beyond what we know. The evidence is etched into data from monumental experiments. Deep underground in Japan, the Super Kamiokande detector, a giant tank of ultra-pure water surrounded by sensitive light sensors, watches for the faint blue flash when a neutrino interacts. In Canada, the Sudbury Neutrino Observatory, using heavy water buried in a nickel mine, provided the definitive proof. These ghosts were caught in the act of transformation. The oscillation itself is a quantum mechanical ballet. It arises because the flavor states we detect, electron, muon, tau, are not the same as the neutrino's true mass states. A neutrino produced in a specific flavor is actually a quantum mixture of three different masses. As it travels, these mass components evolve at slightly different rates, interfering with each other. Over distance, this interference causes the probability of detecting a particular flavor to rise and fall in a smooth, predictable wave. It is as if a red light, while traveling, subtly blended with green and blue, arriving at your eye as a different color entirely. This solved the solar neutrino problem, but it opened a deeper mystery. Precise measurements of these oscillations revealed puzzling anomalies, small deficits, and patterns that did not quite fit the three-flavor model. This has led physicists to a tantalizing hypothesis. What if there is a fourth kind of neutrino, one that is even more ghostly than the others, a sterile neutrino? The three known neutrinos interact via the weak nuclear force, the same force behind radioactive decay. This is how we can, with immense effort, detect them. A sterile neutrino, by definition, would not feel the weak force at all. It would interact only through gravity, making it virtually impossible to catch with conventional particle detectors. It would be a true shadow particle. Why propose something so seemingly undetectable? Because it could explain those stubborn experimental anomalies. In certain reactor and accelerator experiments, the number of neutrinos detected at short distances does not match predictions. The data suggests some neutrinos might be oscillating into this sterile state, and then disappearing from the experiment entirely, like an actor stepping into a fourth, invisible costume and leaving the stage. The implications are staggering. If sterile neutrinos exist and have the right mass, they could be a perfect candidate for warm dark matter, a type of dark matter that was moving fast enough in the early universe to smooth out some of the smallest structures we see. They could also hold the key to another cosmic imbalance: why the universe is made of matter and not antimatter. The oscillations of neutrinos and their antimatter counterparts, antineutrinos, might be slightly different, a process that could have tipped the scales in the universe's first moments, allowing matter to win out. Hunting for these phantoms requires looking in the most extreme places. Experiments like IceCube, a cubic kilometer of Antarctic ice, instrumented with thousands of optical sensors, use the entire planet as a shield. They watch for the extremely rare occasion when a high-energy neutrino from a distant cataclysm, like a black hole jet, interacts in the ice and produces a streak of blue light. By studying the patterns and energies of these events, scientists hope to find a signature that betrays the presence of sterile neutrinos. Other experiments shoot intense beams of neutrinos hundreds of miles through the Earth to massive, distant detectors, meticulously mapping the oscillation pattern for any subtle wiggle that points to a fourth flavor. The story of the neutrino is a lesson in cosmic humility. The most abundant massive particle in the universe, after the photon of light, was once thought to be weightless and static. Now we know it is a shape-shifter with mass, and its oscillations may be a doorway to an entire hidden sector of reality, a realm of sterile shadows that could hold the balance of the cosmos itself. The universe's balance sheet reveals a strange and specific ledger. Right now, in this very cosmic moment, the energy density of dark energy and the combined density of all matter, dark and normal, are almost exactly the same. They are within a single order of magnitude of each other. This is bizarre. Why now? The cosmological constant model of dark energy presents it as a fixed, unchanging property of space. Meanwhile, the density of matter has been plummeting since the Big Bang, as the expanding universe dilutes particles across an ever greater volume. For most of cosmic history,
these two values were wildly different. Matter dominated for billions of years, dictating the universe's expansion rate. Dark energy only began to dominate a few billion years ago, and in the far future, matter density will become negligible, leaving dark energy in complete control. Our present epoch is a fleeting sliver of time where the two are comparable, a brief crossing of the lines on a graph that spans trillions of years. That we exist to witness this precise balance feels like a staggering coincidence, a cosmic why now problem that begs for an explanation. It suggests that perhaps dark energy is not a constant after all. This leads us to a dynamic alternative called quintessence. Imagine dark energy not as a static feature of the vacuum, but as a cosmic field that evolves, a kind of fifth fundamental force that can change in strength over time. This quintessence field could be slowly rolling down a gentle energy slope, its value shifting as the universe ages. More intriguingly, it might even interact with matter in subtle ways. In such a model, the coincidence is not an accident. The evolution of the quintessence field could be tied to the density of matter. As matter dilutes with expansion, the field's properties change, causing its energy density to track alongside matter's for a significant period. The why now becomes because of this. We observe this balance because the dynamics of the field ensure that dark energy becomes dominant around the time-complex structures, and therefore observers like us have had time to form. It is a cosmic feedback loop, where the conditions for life and the behavior of dark energy are subtly linked. Visualize the entire cosmic timeline, from the Big Bang to the distant future. For nearly 10 billion years, the graph shows the matter density line high above a flat, low dark energy line. Then, in a relatively recent and narrow window, the two lines converge and cross. We are living in that crossing. Quintessence proposes that the dark energy line is not flat, but a curve that was designed by the laws of physics to rise and meet the falling matter line at just this point. While elegant, quintessence introduces its own complexities and so far lacks definitive observational proof. Yet it addresses a deep unease among physicists, a sense that our special place in cosmic time is not just a lucky break, but a clue to a deeper, more interactive cosmos where the forces shaping the void are in conversation with the stuff of stars and planets. This cosmic balance sheet is written in a language of unimaginable density and scale. Yet the very fabric that hosts these forces may be scarred by ancient, unimaginably thin flaws. These are cosmic strings, hypothetical one-dimensional cracks in the universe, relics from its first moments of cooling. According to some grand unified theories, as the hot, dense early universe expanded and cooled, it underwent a series of dramatic phase transitions. Think of steam condensing into water or water freezing into ice. Each transition represents a moment when the fundamental forces of nature, which were once unified, split apart into the distinct forces we know today. In that freezing, the fabric of space-time itself could have crystallized imperfectly. Tiny regions might have gotten stuck in the old, high-energy state, unable to transition smoothly with their surroundings. Where these misaligned regions met, they could have trapped an immense concentration of energy, forming a defect. A cosmic string is one such defect, a flaw in the cosmic ice, but instead of a crack in 3 dimensions, it is a flaw in all 4 dimensions of space-time. It is not a string made of atoms. It is a thread of pure space-time curvature, a line where the density is so extreme that a single inch of it could weigh more than Mount Everest. They would be thinner than a proton, yet they could stretch across the entire observable universe, vibrating at nearly the speed of light. Their primary signature would be gravity. A cosmic string warps space-time around it like a massive wire, but in a unique way. Unlike a star or black hole, which creates a symmetric lensing effect, a cosmic string would produce a double image of any galaxy or quasar lying directly behind it. Because space around the string is conical, like a pizza slice removed and the edges glued together, light from a single source would take two different paths around it, arriving at our telescopes as two identical mirror image objects separated by a tiny, precise angle. Astronomers have searched for these perfect cosmic twins in sky surveys, but so far, no definitive candidate has emerged. A more dynamic signature would come from their vibrations. As these monstrous threads whip and oscillate through the cosmos, they would create ripples in spacetime itself, gravitational waves with a very specific, steady frequency. Future observatories, like the space-based LISA mission, could be sensitive enough to hear this faint, persistent hum from the universe's infancy. Their potential role in cosmic history is profound. In the chaotic early universe, the immense gravity of a network of these strings could have acted as a scaffolding, attracting clouds of primordial hydrogen and helium. They would have been the first seeds, the densest knots in the cosmic web, around which ordinary matter could begin to clump, accelerating the formation of the very first galaxies and clusters. They are not just cracks, but possibly the framework upon which the visible universe was built. Visualize the cosmos not as a smooth, expanding sheet, but as a vast, dynamic tapestry. Woven into this tapestry are these unimaginably fine, vibrating threads, each one a fossilized snapshot of a moment when the laws of physics changed forever. They are the scars of creation, hidden in plain sight, waiting for their unique signature to be found in the warped light of a distant galaxy or the faint tremors in the fabric of reality. These cracks in cosmic history exist in a single, definite reality. Yet quantum mechanics, the rulebook for the very small, paints a picture where reality is anything but definite. The most famous interpretation, championed by Niels Bohr and the Copenhagen School, tells us a particle does not have a definite position or state until we measure it. Before observation, it exists in a blurry superposition of all possibilities, a ghostly haze of potential. The act of looking collapses this haze into a single, concrete fact. But this raises a profound question. What is so special about measurement or about a conscious observer? A young physicist named Hugh Everett found this deeply unsatisfying. In the 1950s, he proposed a breathtaking alternative, the many worlds interpretation. Everett's radical idea was this: the wave function never collapses. Every single possible outcome of every single quantum event actually happens. When a measurement is made or any interaction occurs, the entire universe splits, branching like a tree into multiple, equally real copies. In one branch, you see the particles spin up. In another, identically real branch, you see it spin down. The universe did not choose, it took both paths. This is not about parallel universes in distant dimensions. These are new, complete branches of reality that split off from our own, forever separate and unable to communicate. Every time an electron makes a quantum jump, every time a radioactive atom decays, the cosmos undergoes a silent mitosis. The implications are staggering in scale. Every decision you make, from a trivial choice of what to eat for breakfast to a life-altering career move, is not a single choice at all. In the moment of deliberation, your brain is in a quantum superposition of states. When you act, the universe branches. There is a version of you who had the eggs, and another who had the toast. one who took the job offer, and one who turned it down. Every possible history is playing out somewhere in the vast, branching tree of the multiverse. This solves the measurement problem with brutal elegance. There is no collapse because there is no single outcome to collapse to. The observer themselves is split by the process, each copy perceiving a different, definite result. Probability gets a strange new meaning. The reason we see a 50% chance for a coin flip is not because the universe is random, but because we, the specific version of us on this branch, are part of a branching process where our conscious experience follows one path out of many. The other versions of us, with their different experiences, are just as real, but forever out of reach. Contrast this with the Copenhagen view, which requires a mysterious, undefined division between the quantum world and the classical world of measurement. Many worlds removes that division entirely. The entire cosmos, stars, galaxies, and all, is governed by a single, never-collapsing wave function. It is a profoundly lonely and yet populous vision. You are utterly unique on your branch, but you have near infinite copies on others, each living a life diverging slightly from your own. For cosmology, it offers a potential framework for the origin of everything. The initial quantum fluctuation that sparked inflation could have been a branching event from a prior cosmic state. Our entire universe might be one twig on an infinite, fractal tree of cosmic histories. The visual is mind-bending. Picture not a single timeline, but an ever-expanding, shimmering network of possibilities. A tree whose branches are entire universes, each with its own galaxies, its own Earths, and its own versions of you reading these words. It suggests that all the hidden forces we have explored, from dark energy to quantum strings, might themselves have different values or even different forms in other branches. The laws of physics themselves could be a local phenomenon, not universal decrees. While untestable in the traditional sense, the many worlds interpretation forces us to confront the true strangeness of quantum mechanics without resorting to magic. It proposes that reality, in its full glory, is not the single thread we perceive, but an unimaginably vast tapestry, woven from every possibility that quantum law allows. The branching realities of the many worlds interpretation present a cosmos of infinite possibilities, but our own reality is defined by a single, precise trajectory. In the late 1980s, scientists at NASA Jet Propulsion Laboratory noticed something was wrong with the path of two distant spacecraft, Pioneer 10 and Pioneer 11. These robotic explorers, having completed their missions to Jupiter and Saturn, were now hurtling out of the solar system into the dark. By meticulously tracking their radio signals, the team could calculate their exact positions and speeds. The numbers revealed a tiny, persistent anomaly. Both pioneers were slowing down just a fraction more than they should have been. The sun's gravity was pulling them back, but there was an extra, unexplained deceleration, a constant, minuscule tug toward the inner solar system, equivalent to a 10 billionth of the gravity you feel on Earth. This was the Pioneer anomaly, a ghost in the machine that defied explanation for over a decade. For physicists, it was electrifying. Could this be the first crack in Einstein's theory of general relativity? A hint of a new force, or a modification to gravity itself that only became apparent in the vast, quiet expanse of deep space? The anomaly became a rallying point for theorists proposing extensions to general relativity, frameworks now often called modified gravity, or MOG. These theories sought to explain not just the Pioneer drift, but the larger galactic rotation problem, all without invoking dark matter. They suggested that gravity might behave differently at extremely low accelerations or over vast distances, a subtle change in the rules that could account for the motions of spacecraft and stars alike. The idea was compelling, a potential unified solution to two great mysteries. But science has a way of humbling even the most elegant theories. The solution to the Pioneer anomaly did not come from rewriting the laws of physics. It came from an exhaustive, painstaking engineering review. The culprit was not a new force, but an old one, heat. The Pioneer probes were powered by radioactive thermoelectric generators. These units produced electricity from heat, and that heat had to be radiated away into space. Scientists realized that a tiny anisotropic radiation, meaning it was not perfectly even, was emanating from the spacecraft. More heat was radiating from the back of the probe's dish antennas than from the front. This created a minuscule but constant pressure, a photon recoil that acted like a gentle brake, pushing the Pioneers back toward the sun. Once this thermal effect was meticulously modeled and accounted for, the anomalous deceleration vanished. The mystery was solved by a detailed understanding of the spacecraft themselves. This story is a powerful lesson in the scientific process. A tantalizing anomaly sparked brilliant theoretical work, pushing the boundaries of our understanding. Yet, in the end, it was meticulous observation and relentless attention to detail that provided the answer. It underscores why the search for modified gravity explanations of galactic rotation continues, but with greater caution. The Pioneer experience teaches us that before we invoke new physics to explain the cosmos, we must first be certain we have fully understood the physics of our own instruments, the subtle glow of a spacecraft's warmth against the infinite cold. The silent drift of our spacecraft underscores a deeper cosmic silence. If the universe is so vast and ancient, where is everyone? This is the Fermi paradox, a question that grows more haunting the more we learn. With hundreds of billions of stars in our galaxy alone, many older than the Sun, it seems statistically inevitable that other intelligent civilizations should have arisen. They should have spread, built artifacts visible across interstellar distances, or filled the cosmos with signals. Yet we hear nothing, we see nothing. The sky is a profound and unsettling quiet. One terrifying answer to this silence is known as the dark forest hypothesis. It frames the cosmos not as a welcoming community, but as a dark, frozen woodland. Every civilization is a hunter, armed and hidden, moving with absolute caution. To make a sound, to light a fire, is to reveal your position to predators you cannot see. In such a forest, the only safe strategy is silence. The hypothesis rests on a few grim assumptions about cosmic sociology. First, that all civilizations prioritize survival above all else. Second, that the distances between stars make trust impossible. You can never truly know another civilization's intentions. And third, that technological advancement inevitably leads to a capability for total destruction, perhaps with relativistic weapons or self-replicating probes. Given these conditions, the logical move is preemptive strike. If you detect another civilization, especially one less advanced, the safest course is to eliminate it before it becomes a threat. This creates a universe where any broadcast, any beacon announcing we are here, is a death sentence. It explains the great silence not as an absence of life, but as a universe filled with life that has learned to hide. Our own efforts, like the messages sent from the Arecibo telescope or the golden records on the Voyager probes, could be seen not as hopeful greetings, but as dangerously naive shouts into a forest we do not understand. This chilling logic transforms our view of cosmic forces. The hidden dynamics shaping the universe are not just physical, like dark energy or quantum loops. They are also sociological, driven by fear and competition on a galactic scale. The most powerful force in the cosmos might not be gravity, but suspicion. It suggests a universe where intelligence is not a spark that spreads light, but a flame that must be carefully concealed, lest it attract a darkness that snuffs it out forever. In this dark forest, the stars do not twinkle with promise. They glint like the eyes of hidden watchers, and the silence between them is not empty, it is listening. The profound silence of the cosmos forces us to look inward, to the one instrument we have for perceiving it all. What is consciousness, and could its origins be entangled with the quantum fabric of the universe itself? This is the realm of quantum consciousness, a theory that bridges the gap between mind and matter in the most radical way imaginable. It suggests that our awareness is not merely a byproduct of classical brain chemistry, but a phenomenon rooted in the strange, probabilistic world of quantum mechanics. The most detailed proposal comes from physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff in a model called orchestrated objective reduction, or ORCH. Their hypothesis begins with a specific structure inside our brain cells. Deep within the neurons are tiny cylindrical scaffolds called microtubules, part of the cell's skeleton. In the classical view, neurons simply fire like biological switches, but Hameroff proposed that microtubules are far more sophisticated. They could act as quantum computers, their lattice structures capable of housing quantum information. Within these tiny, warm, wet tubes, electrons could exist in superposition, occupying multiple states at once, performing complex calculations. Penrose then provided the other crucial piece. He argued that the collapse of these quantum superpositions, the moment a probability wave resolves into a definite state, is not random. He proposed it is an objective process tied to the fundamental geometry of spacetime, a moment of genuine, non-computable choice in the universe. In the ORCH model, consciousness is this orchestrated collapse. As quantum computations in the brain's microtubules reach a certain threshold, they undergo objective reduction, and each such event is a moment of conscious experience, a flicker of awareness. These micro-events then orchestrate across vast networks of neurons to produce our seamless stream of thought. It is a breathtaking idea. It places the seat of consciousness not in the firing of neurons, but in the quantum vibrations within them, suggesting our minds are in direct dialogue with the foundational level of reality. To visualize this, picture the brain's intricate networks not as wires carrying electrical pulses, but as shimmering webs of quantum light, with tiny collapses sparking like fireflies in the dark, each spark a fragment of a feeling, a color, a memory. This theory, however, stands in stark opposition to mainstream views. Most neuroscientists see the brain as a warm, noisy, and chaotic place, utterly hostile to delicate quantum states, which we usually only observe in ultra-cold, isolated laboratory conditions. They argue that quantum coherence, where particles act in unison, would be destroyed almost instantly in the bustling environment of a living cell. Furthermore, critics point out that consciousness could well be an emergent property of complex classical neural networks, with no need for quantum mystery. The debate is fierce, highlighting the vast gulf between our understanding of the very large, the very small, and the very conscious. Yet, as a speculative frontier, quantum consciousness forces a profound question. If even a part of our awareness is quantum, then the observer in quantum physics is not separate from the system. We are not looking at the quantum world from outside. We are of it. Our thoughts, our choices, our very sense of self might be woven from the same uncertain threads that stitch together reality. It hints that the final hidden force we must understand may not be out in the dark between galaxies, but within the luminous darkness of our own minds. The idea that consciousness itself might be quantum adds a terrifying new layer to an old cosmic riddle. If our minds are simply patterns of information, then what is to stop the universe from assembling that pattern by pure random chance? This is the Boltzmann brain paradox, a thought experiment that pushes our understanding of reality to the brink of absurdity. It is named for Ludwig Boltzmann, a 19th century physicist who helped develop statistical mechanics. He proposed that in a vast, eternal universe, even the most unlikely events will eventually happen given enough time. The paradox applies this logic to observers like us. In an infinitely old or eternally fluctuating cosmos, the random jostling of particles will, by sheer accident, eventually assemble a fully formed, self-aware brain, complete with false memories of an entire life and a universe that never actually existed. According to the statistics, such a freak fluctuation is vastly more probable than the gradual, ordered evolution of an entire 14-billion-year-old cosmos with galaxies, planets, and a continuous history. It is more likely for a single, conscious brain to pop into existence in the void than for the immensely complex universe we perceive to be real. Picture the ultimate isolation. A lone, disembodied brain floats in an infinite, empty darkness. It is not in a body, not on a planet. It is a perfect, self-contained illusion. Within its neural circuitry, electrical patterns fire, constructing a phantom reality. It recalls a childhood home it never had, the warmth of a sun that does not exist, and the memory of watching this very video. It believes it is part of a vast, ordered cosmos, but that cosmos is a fiction, a detailed hallucination generated by a random quantum accident in an otherwise dead and empty eternity. This is the Boltzmann brain, and its existence is a statistical prediction of certain cosmological models, particularly those involving an eternal, steady-state universe or a cosmos that eventually reaches heat death and then fluctuates over infinite time. The paradox strikes at the heart of cosmology and the nature of observation. If we are typical observers, then we should find ourselves in the most common kind of conscious experience. The overwhelming majority of conscious experiences, according to this statistical logic, would be these brief, disembodied hallucinations in the void, not the rare, sustained experience of a real, evolving universe. Therefore, the fact that we perceive a coherent, long-lasting, and richly structured reality is powerful evidence against those cosmological models that predict Boltzmann brains are inevitable. Our ordered experience is an anomaly that the universe must explain. This has forced physicists to rule out certain models of eternal inflation or cyclic universes if they lead to a prediction where Boltzmann brains outnumber ordinary observers like us. Our very perception of continuity becomes a data point that constrains the shape of all reality. It is a dizzying hall of mirrors. To trust our observations about dark energy, the Big Bang, or the multiverse, we must first assume we are not just a momentary glitch in an eternal silence. The paradox forces a choice. Either our cosmological theories are wrong because they predict we should not exist as we are, or there is something fundamentally special about our kind of ordered, embedded consciousness. Some physicists argue it points to a universe with a definite beginning and an end, a cosmic story with a clear timeline that prevents these infinite fluctuations. Others see it as a reductio ad absurdum, showing the limits of applying pure probability to questions of existence and observation. The Boltzmann brain is the ultimate skeptic, whispering that every piece of data, every memory, every law of physics you think you have discovered could be nothing more than a fleeting, tragic coincidence in the dark. The universe's fundamental code appears beautifully simple, yet it holds a glaring and potentially fatal flaw. Our standard model of particle physics is a masterpiece, describing every known particle and force with breathtaking precision. But it contains a ticking time bomb, a problem of naturalness concerning the Higgs boson. The Higgs gives other particles their mass, but its own mass is incredibly delicate. According to quantum theory, it should be receiving enormous corrections from virtual particles. Corrections so large they would drive its mass up to the scale of the entire universe. For the Higgs to remain as light as we observe, these titanic contributions must cancel out with a precision of 1 part in a billion billion. It is as if you dropped a feather from a skyscraper and it landed exactly on a predetermined spot, despite a hurricane raging all around. This absurd fine-tuning suggests something is missing, a hidden symmetry that protects the Higgs. That something could be supersymmetry. Supersymmetry, often called sussy, is one of the most elegant extensions ever proposed for the laws of physics. Its core idea is stunningly simple. For every known particle in the Standard Model, there exists a superpartner. Every quark, every electron, every photon has a hidden twin. These superpartners would differ by half a unit of spin, a fundamental quantum property. Fermions, the matter particles like electrons and quarks, would have bosonic superpartners. Bosons, the force carriers like photons and gluons, would have fermionic superpartners. The names follow a charming convention. Add an S for the bosonic partners, like the selectron for the electron, or the squark for the quark. For the fermionic partners, add ino, like the photino for the photon, or the gluino for the gluon. This symmetry doubles the particle zoo, populating the cosmos with a shadow realm of superparticles. The beauty of sussy is that it naturally solves the Higgs problem. In the equations, the contributions from ordinary particles and their superpartners come with opposite signs. If supersymmetry were perfect and unbroken, these contributions would cancel each other out exactly, leaving the Higgs mass stable and light without any need for miraculous fine-tuning. The hurricane's winds would perfectly counterbalance each other, letting the feather land gently on its mark. But we do not see these superpartners in our everyday world. An electron's superpartner, the selectron, would have the same mass as the electron if the symmetry were perfect. We would have detected it long ago. This means supersymmetry must be a broken symmetry. The superpartners are thought to be immensely heavy, explaining why they have not yet shown up in our particle colliders. Their great mass is what hides them from our current view. Beyond saving the Higgs, supersymmetry offers other profound gifts. It provides a compelling pathway to the grand dream of physics, the unification of all forces. In the Standard Model, the strengths of the electromagnetic, weak, and strong forces do not quite converge at high energies. But when you include the contributions of superpartners in the calculations, the 3 lines meet at a single, elegant point. It suggests that at the incredible energies of the early universe, all forces were one, a unified superforce described by supersymmetry. Perhaps most tantalizingly, sussy offers a perfect candidate for dark matter, the lightest supersymmetric particle, often thought to be the neutralino. This particle is stable, electrically neutral, and only interacts weakly, ticking every box for a WIMP-like dark matter particle. It would have been forged in the heat of the Big Bang and persist today as the invisible scaffolding of galaxies. For decades, supersymmetry was the darling of theoretical physics, an elegant framework that promised to solve multiple cosmic puzzles at once. The stage for its discovery was set at the world's most powerful particle smasher, the Large Hadron Collider. Many physicists expected that when the LHC reached its full energy, it would open a door to the supersymmetric world, revealing a selectron, a squark, or a gluino. But the collider has remained silent. Despite smashing protons together at unprecedented energies and sifting through mountains of data, no definitive sign of a superpartner has emerged. The simplest, most elegant versions of supersymmetry have been ruled out. The superpartners, if they exist, are heavier than many had hoped. This non-discovery has cast a long shadow. Some researchers have moved on, exploring other ideas, while others have adapted, proposing more complex and nuanced versions of SUSY where the superpartners are just beyond our current reach, or where they decay in ways that are harder to spot. The dream is not dead, but it has been deferred. The search continues at the LHC and in deep underground detectors listening for the neutralino. Supersymmetry represents a breathtaking vision of cosmic balance, a hidden mirror world that stabilizes our reality and whispers of a deeper unity. Its absence in our experiments so far is not a failure, but a guidepost, telling us that if this elegant symmetry is woven into the universe, it is hidden in folds of energy and complexity we are only beginning to probe. The silence of our particle colliders speaks of hidden symmetries, but a faint chill in the oldest light of all tells a different story. Etched across the cosmic microwave background, the afterglow of the Big Bang is a mysterious and immense cold spot. This region of sky, in the constellation Eridanus, is significantly colder than our models predict, a vast, subtle bruise on the infant universe. It is not a random fluctuation. Its size and temperature deficit make it a genuine anomaly, a cosmic outlier that should not exist according to our standard understanding of the universe's smooth, uniform beginnings. One leading theory attempts to explain this chill with a cosmic emptiness. Imagine a photon, a particle of light, from the cosmic microwave background, traveling toward us for over 13 billion years. According to general relativity, as a photon climbs out of a gravitational well, it loses energy, a phenomenon called gravitational redshift. Now, picture its journey passing through a truly gargantuan region of space, a supervoid, an area hundreds of millions of light years across containing far fewer galaxies and clusters than the cosmic average. This supervoid would be a shallower gravitational well than the denser universe around it. As the photon enters this vast underdense region, it must climb down into this shallow well, which gives it a tiny boost of energy. But then, to exit the void and continue to us, it must climb back out, losing that energy again. However, because the universe has been expanding during the photon's multi-million-year trip through the void, the well itself is changing. The net effect is that the photon loses a little more energy climbing out than it gained climbing in. It emerges slightly redshifted, which we perceive as a colder temperature. This is the integrated Sachs-Wolf effect, and a supervoid of the right scale and emptiness could, in theory, produce the cold spot we observe. Astronomers have indeed found a large, underdense region in the direction of the cold spot, but here is the puzzle. The supervoid we have found, while enormous, does not seem quite large enough or empty enough to explain the profound chill. The numbers do not fully add up. This mismatch opens the door to far more exotic possibilities. What if the cold spot is not a shadow cast by an absence, but a scar from a violent encounter? In the theory of eternal inflation, our universe is one bubble in a frothing multiverse. These bubbles can sometimes collide. If, in the earliest moments of our cosmos, our expanding bubble universe grazed another, the energy released at that boundary could have left an imprint on the cosmic microwave background. The cold spot could be the cosmic bruise from that primordial collision, a dent in our reality caused by brushing against another. Visualize it as two soap bubbles in a sink, gently touching. Where they meet, the surface of each bubble is distorted. In our universe, that distortion imprinted itself as a region of altered temperature, a fossilized handshake from a neighbor we can never otherwise see. Maps of the cosmic microwave background, like those from the Planck satellite, show this feature with stark clarity. The rest of the sky is a modeled map of tiny red and blue variations, the quantum seeds of all future structure. But there, in one sector, is a large, coherent patch of deep blue, a cold ocean in a sea of warmer noise. It stands out, a question mark written in the language of primordial heat. The investigation continues, with astronomers mapping ever larger volumes of the universe to better measure the proposed supervoid, and theorists refining models of bubble collisions. The cold spot remains one of the most tantalizing anomalies in modern cosmology. It is a reminder that our cosmic map may still contain uncharted territories, places where the smooth story of inflation is punctuated by an event so colossal, it left a mark on the very fabric of the newborn cosmos. A cold spot in the ancient sky hints at collisions with other realities. But what if our own universe contains particles that shatter the most fundamental speed limit of all? This is the realm of tachyons, hypothetical particles born from a simple, radical twist in the equations. In Einstein's theory of special relativity, nothing with real mass can ever reach the speed of light. As an object accelerates, its mass effectively increases, requiring more and more energy to go faster, approaching infinity as it nears light speed. The cosmic speed limit is absolute. Tachyons turn this logic inside out. They are proposed to be particles that always travel faster than light. They cannot slow down to light speed or below it. For them, the light barrier is not a ceiling, but a floor. This bizarre property comes from their most defining feature, imaginary mass. In mathematics, the square root of a negative number is called an imaginary number. If you plug an imaginary mass into the equations of relativity, you get a particle whose speed is always greater than light. It is a purely theoretical construct, a ghost in the machinery of physics that allows for a consistent, if unsettling, mathematical solution. Their theoretical properties are as strange as their origin. Because they travel faster than light, they would experience time backwards relative to us. A tachyon moving from point A to point B would, from its own perspective, arrive before it left. This is where the paradoxes begin, and they are catastrophic for our understanding of cause and effect. Imagine a tachyon-based communication device. You could send a signal to your own past. You receive a message that says, "Do not send the message." If you obey, you never send it. So how did you receive it? If you ignore it and send it anyway, you create a logical loop with no origin. This violates causality, the principle that cause must always precede effect. It unravels the logical sequence of the universe, making events impossible to untangle. For this reason, most physicists consider tachyons unlikely to exist in reality. They are seen not as predictions, but as mathematical curiosities that highlight the stability of our current laws. The fact that tachyons lead to such profound paradoxes is taken as evidence that nature forbids them, protecting the integrity of time and causality. Yet, they have not been completely banished from speculation. In some advanced quantum field theories, tachyons occasionally appear not as physical particles, but as signals of an unstable vacuum. Their presence in the math indicates a system that is not in its lowest energy state and wants to decay into something more stable, much like the false vacuum we discussed earlier. In this context, a tachyon is not a thing to be detected, but a warning sign in an equation. They also hold a persistent place in science fiction, often as plot devices for time travel, instant communication, or exotic propulsion. Their appeal is obvious. They represent a key to unlocking the ultimate speed limit, offering a doorway to the stars or to the past. But in the cold equations of reality, that doorway seems locked by the very fabric of causality itself. The search for them has been unequivocally negative. If tachyons interacted with ordinary matter, even weakly, they would produce a distinctive type of radiation as they lost energy in a medium, something called Cherenkov radiation for superluminal particles. No experiment has ever detected such a signature. Their non-existence is a silent guardian of cosmic order, ensuring that the arrow of time points relentlessly forward, and that every effect has a cause that lies firmly in its past. Our universe may not be expanding into an infinite void, but falling into a deeper abyss. This is the startling speculation that our entire cosmos, with all its galaxies and dark energy, exists inside the event horizon of a colossal black hole belonging to a parent universe. The mathematics hint at a bizarre symmetry. The equations describing the collapse of a massive star into a black hole are hauntingly similar to those describing the expansion of our universe in reverse. In a collapsing star, matter and energy are crushed toward an infinitely dense singularity. Flip the arrow of time, and you have an explosion from an infinitely dense point, a Big Bang. This mirror image has led some theorists to wonder if they are not just similar, but the same event seen from different perspectives. From the outside of a black hole in the parent universe, matter vanishes behind an event horizon, crushed to a point of no return. But from the inside, that point of no return could be the beginning of everything. The singularity that forms in the heart of a black hole might not be an end, but a bridge, a white hole birthing a new spacetime continuum. Our Big Bang could have been the moment a star collapsed in another reality, its interior rebounding as an entirely new cosmos. This idea finds a powerful echo in the holographic principle. Recall that all the information within a black hole is encoded on its two-dimensional surface. If our universe is the interior of a black hole, then all the information about every galaxy, every planet, and every one of us is not truly within our three-dimensional space. It is painted on the spherical boundary of our cosmos, the cosmic horizon where light from the Big Bang first reaches us. We are not looking out at the universe from within. We are living inside a projection. The three-dimensional reality we experience is a holographic rendering of data stored on the two-dimensional shell of our cosmic prison, or our cosmic womb. The conceptual appeal is profound. It offers a potential origin story that requires no separate mechanism for creation. The universe is not a singular, inexplicable event, but a natural byproduct of the life cycle of matter in a higher dimensional reality. Every black hole could be a gateway to a new universe, making our cosmos just one link in an infinite chain of cosmic reproduction, a fractal nesting doll of realities. Yet the theory faces monumental challenges. The most glaring is scale. The black holes we observe in our universe have event horizons with a specific size based on their mass. The observable universe, if it were inside a black hole, would imply a specific density. Our universe's average density is far, far lower than what you would calculate for a black hole of its size. To make the numbers work, you must invoke extra dimensions or different physical constants in the parent universe, moving the goalposts into untestable territory. Furthermore, our universe is geometrically flat on large scales, while the interior of a standard black hole is not expected to be. And then there is dark energy, the force accelerating our expansion. A simple black hole interior would eventually collapse, not accelerate outward forever. So the model requires significant, complex tweaks to account for what we see. It remains a captivating thought experiment, a poetic vision of cosmic ancestry. It suggests that every time a star dies in a spectacular collapse somewhere in the multiverse, it does not leave emptiness. It leaves a legacy, a whole new universe flowering in the darkness, its laws of physics set by the chaotic conditions of that collapse. We may be the children of a forgotten giant's final breath, living out our cosmic history on the inner surface of its ultimate shadow. The universe may be more than a cold machine of particles and forces. Perhaps it is a living, breathing entity. This idea finds its roots in a beautiful and controversial theory about our own planet, the Gaia hypothesis. Proposed by chemist James Lovelock and biologist Lynn Margulies, it suggests Earth's biosphere is not just a passive collection of life on a rock. It is a vast, self-regulating system, a superorganism where living organisms and their inorganic environment are tightly coupled to maintain conditions suitable for life. The forests, oceans, and microbes actively work to stabilize global temperature, atmospheric composition, and ocean salinity, creating a planetary homeostasis. Now, take that profound interdependence and stretch it across the cosmos. Could life and intelligence be not a rare accident in a dead universe, but a fundamental, driving feature of cosmic evolution itself? This is the speculative leap of cosmic Gaia, a vision where biology is woven into the fabric of physics. Imagine a galaxy not as a mere whirlpool of stars and dust, but as a complex, evolving ecosystem. Within its spiral arms, stars are born and die, seeding space with the heavy elements essential for planets and life. The energy flows from these stars, the gravitational interactions between solar systems, the vast magnetic fields, all could form a kind of galactic metabolism. And life, once it emerges on countless worlds, might begin to influence this metabolism on a grand scale. An advanced civilization, for instance, might learn to harness the energy of its star, not just for its own survival, but to perform some function within the galactic system, perhaps even stabilizing it against certain instabilities. In this view, intelligence becomes a cosmic organ, a tool for regulation and complexity on the largest scales. This leads to a staggering philosophical implication. The fundamental constants of nature, the precise numbers that allow atoms and stars to form, might not be arbitrary or the result of a multiverse lottery. They could be the way they are because those values are necessary for the emergence of life and, ultimately, of cosmic consciousness. Life is not a passenger in the universe. It is the purpose, the universe becoming aware of itself in order to guide its own destiny. This is the ultimate anthropic principle, not as a statistical selection effect, but as a teleological drive. The cosmos evolves toward states that foster observers because observers are part of its growth, like a tree evolving leaves to capture sunlight. Contrast this with the purely mechanical theories we have explored. In the standard model, dark energy is a property of empty space. Dark matter is a collisionless particle, and the universe expands according to fixed equations. It is a clockwork universe, beautiful in its deterministic logic, but ultimately silent and unconscious. The cosmic Gaia hypothesis injects a narrative of meaning and agency. It suggests the hidden forces we detect, the acceleration of expansion, the missing mass, might be influenced or even orchestrated by the collective activity of life across billions of years and billions of galaxies. The universe is not just a place where life happens. It is alive, of course. This remains a poetic speculation far from testable science. It risks veering into mysticism, attributing intention to blind processes. Yet, as a philosophical counterpoint, it is powerful. It challenges the cold loneliness of the cosmic dark forest and the sterile probabilities of the multiverse. It offers a story where we are not isolated, accidental sparks in an infinite void, but integral participants in a grand, unfolding biosphere of galactic scale. Our search for meaning in the stars might not be a projection, but an intuition of our true role. The universe may be whispering that its greatest hidden force is not in the void, but in the living, questioning mind that strives to understand it. The search for meaning and mechanism leads us to the ultimate frontier of thought. Across all these 30 theories, from the dark forest to cosmic consciousness, runs a single unifying thread, the human desire to find one single story that explains everything. This is the dream of a theory of everything, a final, elegant framework from which all forces, all particles, and all of reality's rules can be derived. It is the quest to write the universe's source code. For over a century, physics has been a story of unification. First, electricity and magnetism were woven together into electromagnetism. Then, electromagnetism and the weak nuclear force were unified into the electroweak force. The great goal is to complete this tapestry, to bring the strong nuclear force and, most challengingly, gravity into a single, beautiful equation. This final unification would describe the universe at its most fundamental level, the unimaginably tiny Planck scale, where the fabric of space-time itself is believed to be a seething quantum foam. At this scale, a trillion times smaller than a proton, our current concepts of space and time break down. A theory of everything would give us the rules for this domain, the grammar for the quantum grammar of reality. The two most prominent paths we have explored, string theory and loop quantum gravity, are both attempts to reach this summit, though they climb from opposite sides of the mountain. String theory proposes that the fundamental objects are vibrating strands in a 10 or 11-dimensional arena, with gravity emerging naturally from their harmonies. Loop quantum gravity suggests that space itself is woven from discrete, quantized loops, with gravity baked into the geometry of this spin network. Both seek to marry quantum mechanics with general relativity, but their languages and starting points are profoundly different. One builds reality from strings in a pre-existing space. The other builds space itself from loops. Finding a theory of everything would be more than a technical triumph. It would reshape our understanding of every hidden force we have discussed. Dark energy might be revealed as a specific vibration of the cosmic strings or a dynamic feature of the evolving quantum geometry. Dark matter could be identified as a specific particle in the extended family of a unified theory, like the lightest supersymmetric particle, or it might dissolve entirely, explained as a subtle gravitational effect emerging from the theory's equations. The origin of the universe, whether a bounce, a bang, or a bubble collision, would be described with mathematical precision, removing the singularity and giving us a clear picture of cosmic genesis. Such a theory would offer a single lens through which to view the entire cosmos, from the furious quantum jitter at the heart of a black hole to the serene, accelerating expansion of the galactic horizon. It would tell us if extra dimensions are curled up at every point, if the multiverse is an inevitable prediction, or if our universe is truly alone and unique. The implications for technology are beyond our current imagination, potentially unlocking an understanding of energy and spacetime that seems like magic today. Yet the pursuit itself, regardless of the final answer, is a testament to something profoundly human. For thousands of years, we have looked at the stars and wondered. We have built instruments to listen to the whispers of the cosmos, from radio telescopes to particle colliders buried deep underground. Each theory, even those that are eventually proven wrong, is a step on that path. They are stories we tell to make sense of the darkness, narratives of hidden forces and secret symmetries that help us map the unknown. Picture, if you can, a single, shimmering equation, brief enough to fit on a t-shirt, yet deep enough to contain the entire history and destiny of the cosmos. Within its elegant symbols would be the recipe for every galaxy, every atom, every force that pushes and pulls at the fabric of existence. It would be the ultimate answer to the question that has driven this entire journey, a complete description of the universe's hidden architecture. That is the dream that fuels the search, a beacon of understanding in the vast and mysterious dark. From the relentless push of dark energy to the silent hum of action fields, this journey across 30 frontiers reveals a cosmos teeming with hidden architecture. We have traced the ghostly contours of dark matter, walked the vibrating strings of higher dimensions, and peered into the holographic illusion of our own reality. Each theory, from the well-tested pillars of cosmic inflation to the speculative whispers of simulation and consciousness, represents a courageous attempt to map the unknown. This exploration is not about finding final answers today. It is about the act of questioning itself, about pushing the very boundaries of what it means to understand. It is a testament to our species' refusal to accept the darkness without trying to light a candle. So, which of these hidden forces resonates most deeply with you? Was it the cosmic loneliness of the dark forest, the elegant dance of supersymmetry, or the mind-bending possibility that we live inside a black hole? Share your favorite theory in the comments below. The story of the universe is still being written, and every one of these ideas holds the potential to become a cornerstone of tomorrow's physics. To continue exploring the greatest mysteries of space, time, and reality, be sure to subscribe. The